Now we want to use our important fact that convolution in time is multiplication in the Laplace domain to find the output of LTI systems using the Laplace transform. So our learning objectives are to find the Laplace transform of a system output given the input and impulse response, and then to use partial fraction expansion to get the time domain output signal. So let's remember our most important fact, which is that if y of t is the convolution, time domain convolution of an impulse response h and an input signal x, then y of s, the Laplace transform of the output, is the multiplication of h of s times x of s. So x of t goes to x of s, h of t goes to h of s under the Laplace transform with ROCs rx and rh. And if there's no pole zero cancellation, then the output ROC is the intersection of the two ROCs of the input and the impulse response. Okay, so let's do a little example. Suppose x of t is e to the minus 2t u of t, so we know that this is going to Laplace transform to 1 over s plus 2, that we get over here. And h of t is minus e to the minus t u of t, that's going to give us minus 1 over s plus 1, and e to the minus 3t u of t, add that in, and we're going to get s plus 3, 1 over s plus 3. This has ROC real part of s greater than minus 3, but this one has ROC real part of s greater than minus 1, and so the intersection of those is going to give us the real part of s is greater than minus 1. Right here. So if we take h of s and we cross multiply, we multiply the s plus 3 by minus 1 and the 1 by s plus 1 and gather terms, we get minus 2 over s plus 1 times s plus 3. So now if we want to compute the system output, what should we do? Well, we just multiply h of x and x of s. So we're going to get minus 2 over s plus 1 plus times s plus 2 times s plus 3. And the ROC is going to be the intersection of the ROCs here, which is going to be essentially the smallest ROC, which is the real part of s greater than minus 1. Okay, so now to get the time domain signal, we're going to use partial fraction expansion. To get the s equals minus 1 term, we cancel out the s plus 1 and plug in s equals minus 1, and similarly for minus 2 and minus 3. And we're going to get these numbers, minus 1, 2, and minus 1. You can verify that for yourself. Okay, so now we have to convert back to the time domain. That's the next step in the problem. So we have to therefore look at the ROC, which is the real part of s is greater than minus 1. So this is what the pole zero diagram for y of s looks like. It's got 3 poles, and we have the region of convergence is the real part of s greater than minus 1. So it's this green region here. We can write out in the formula for the Laplace transform, y of s is equal to minus 1 s plus 1 plus 2 over s plus 2 minus 1 over s plus 3. And then we just convert each term back to the time domain. We're looking at right-sided signals because the ROC is a right half plane. So we're going to take all right-going signals, which means we're going to have the u of t versions of these signals, not the u of minus t versions of these signals. So we get minus e to the minus t u of t plus 2 e to the minus 2t u of t and minus 1 times e to the minus 3t u of t. Now the question is this faster than using our formulas that we had before for CT convolution? And the answer is maybe. But we can do an example where it's clearly going to be advantageous to use the Laplace transform. And in general, using the Laplace transform method is convenient and can be a fast way to do simple system output calculations. So here's an example with a cosine and a decaying exponential. So now we want to find y of t and y of s and the ROC of y of s. So again, first step is to take the Laplace transforms of x of t and h of t. This cosine, we get s over s squared plus 1. It's because the omega naught is equal to 1. And h of s, we get 1 over s plus 3 because it's e to the minus 3t. The region of convergence for x of s is the real part of s is greater than or equal to 0 because we have the pole zero diagram remember the pole zero diagram looks like this for x, and so this is the region of convergence. And similarly for h, we're going to have dot 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 dot. Here's -3, and we're going to have the region of convergence look like this. So we're going to get the intersection of the two as the region of convergence. So we multiply the x of s and h of s, and we get this s over s squared plus 1 times s plus 3, and then we can factor them out into poles. So we get a pole at minus j, a pole at plus j, and a pole at -3, and a 0 at 0. Okay, so now we can do partial fraction expansion, this time with complex numbers. It's the same deal using complex numbers versus real numbers. So we cancel out the s minus j term in the denominator and plug in s equals j, and we get j over 2j times j plus 3. We cross multiply, don't forget that j is in the numerator, and we get 1 over 6 plus 2j, and I'm going to define this 1 over 6 plus 2j, I'm going to define this to be alpha. And why is that? Because if we do the same thing for the root at minus j, and you do all the algebra out here, you get to see that the corresponding coefficient there is going to be alpha star, is just the complex conjugate of alpha. And then for the final root, we plug in s equals -3. We have -3 plus j and -3 minus j. Those two are conjugates of each other, so we get the magnitude squared of -3 plus j, and that's 10. And then up top we get the -3 that we plugged in for s. Okay, so y of s is equal to alpha over s minus j plus alpha star over s plus j minus 3/10 over s plus 3. We gather like terms. We get an s squared plus 1 in the denominator, and we have alpha plus alpha star times s. A complex number plus its conjugate is going to be real. And then we get j alpha minus j alpha star and conjugate, and that's also going to give us a real number. So that's good, because we convolve two real signals, we should get a real signal at the output. Okay, so what is this magical alpha? It was 1 over 6 plus 2j. So now we have to multiply by 1 over 6 minus 2j, top and bottom. So we get 6 minus 2j, and we see that this magnitude squared is going to be 36, which is equal to 6 squared plus, so 6 squared plus 2 squared, which is equal to 36 plus 4 is equal to 40. So we're going to get 6 over 40 minus 2 over 40, so that's 3/20 minus 1/20 j. So then we take alpha plus alpha star, and we get 3/10, because we get twice this real part here. This is equal to twice times the real part of alpha. And then j alpha minus j alpha star, we're going to get 2 over 20th, or 1/10. This is actually twice the imaginary part of alpha star. So we plug this in, we get 3/10 s plus 1/10 over s squared plus 1. So this is going to give us, this first term is going to give us a cosine. The second term is going to give us a sine. And then we have an s plus 3. This is going to give us e to the minus 3 t. So let's see what that looks like in the end. So in the end, we have y of s. This is our y of s term again. Remember, our ROC is a real part of s greater than 0. So we're going to use our two transform pairs, that the cosine goes to s over s squared plus 1, and the sine goes to 1 over sine squared plus 1. So we're going to get 3/10 times cosine t u of t plus 1/10 times sine t u of t minus 3/10 times e to the minus 3t u of t. Okay, we did a lot of algebra. We can pat ourselves on the back, worked with complex numbers, can feel good about ourselves, but really need to understand what happened here. So what did we actually show? We put in a cosine. We had a decaying exponential as the impulse response. What we got out was a cosine, a sine, and a decaying exponential. And so we can see that the impulse response, the decaying exponential mode, we can think of it as e to the minus 3t. That appears in the output. But what happens is the cosine is phase shifted to give both a cosine and a sine part. So we get this real sort of, we get the cosine, and we also get a phase shifted cosine. And so this is this example kind of shows that when you have complex roots, you can get more complicated behavior when you look at the convolutions of signals in the time domain. You can see from the Laplace domain why you get sort of complicated outputs in the time domain. As always, try to do some examples yourself. So try to find the output time domain signals for these pairs of x's and h's. And just as a warning, for some of these, you're going to have to do some kind of messy partial fraction expansions. The last one is going to be a little bit messier because of this e to the minus t cosine t. It's going to have a much more complicated formula for the Laplace transform. But again, doing these types of problems will help build some intuition and also build some facility with working with Laplace transforms and also partial fraction expansion.